Okay, so if you have f of g of x, the composition, f is the outside, g is the inside, right? And once again, the derivative of the composition f of g of x is equal to the derivative of the outside evaluated at the inside multiplied by the derivative of the inside. And let's look at another example today. So let's say I have the function g of x given by the function 1 over x squared plus x plus 1 to the power 2/3. So let's say I have that function. So how would I take the derivative? Yes, I can apply the quotient rule. However, it's going to be easier just to do the following. You can write this as what? Negative 2/3. And now you look at this function again. You wish that x squared plus x plus 1 was what? Just x. So in fact, when you look at this function is the composition of the function x to the negative 2/3 and the function x squared plus x plus 1. So if you take the composition of x to the negative 2/3 and x squared plus x plus 1, you get the function g. Okay? The outside being x to the negative 2/3, the inside being this x squared plus x plus 1. Notice that if you plug in x squared plus x plus 1 here, you get the function that we are looking at, right? Is that making sense? You plug in this function for x, you get the function that we are looking at. So by the chain rule, what's the derivative? By the chain rule, then the derivative is given by the derivative of the outside function, right? So you take the derivative by assuming that x squared plus x plus 1 is x. So by assuming your wish, you just take the derivative. So this would be what? Negative 2/3 times x squared plus x plus 1 to the exponent what? Negative 2/3 minus 1, and then you multiply by the derivative of the inside function, or it's the derivative of the quantity that you wished to be x, right? So what's the derivative of that? 2x plus 1. Is everybody okay with that? And you can simplify a little bit by simplifying the exponent here. So this would be negative 2/3 x squared plus x plus 1 to the what? Negative 5/3 times 2x plus 1. And you can stop right there, but you can also rewrite this as negative 2 times 2x plus 1 over 3 times x squared plus x plus 1 to the 5/3. Just the negative exponent can be written in this way. Is everybody okay? Is that okay? Alright, so that's the derivative in this case. Now, in practice, people write in many places people write the chain rule in a different notation. So let's let y be the function g of x, and let's let z be the function f of y, right? And then what can we say about z? We can say that z is f of g of x, right? Is that right? If z is f of y, y is g of x, then z is f of g of x. So, okay, if I now say what's the derivative of z with respect to x, that's basically asking you what's the derivative with respect to x of f of g of x, right? And then by the chain rule, what is that? It is the derivative of the outside evaluated at the inside times the derivative of the inside, right? Now, this is the same as the derivative of g of x. Remember, we are denoting g of x by y. And what is f prime of y? I can write f prime of y as dz dy, right? I can write f prime of y. Remember, another notation for that would be dz dy. And what would be a notation for g prime of x? dy dx, right? dy dx represents g prime of x. So if I write that, here I get dz dy here, and then I get dy dx here. So at the end, what we are getting then is that the derivative of z with respect to x is equal to the derivative of z with respect to y times the derivative of y with respect to x. So this is in fact the chain rule in just in a different notation, okay? So this is the chain rule. This is also the chain rule, but in a different notation. And in practice, in physics and other places, often people like to use that notation, and it's really helpful to use that. So basically, suppose you have an applied problem where you have three variables x, y, and z. You have a problem in application where you have three variables x, y, and z. You need to know that the derivative of z with respect to x. You need to know the rate of change of z with respect to x. But somehow you don't have a direct formula for z in terms of x. So maybe you have a direct formula for z in terms of y, and you can find the derivative of y with respect to x. Okay. So let's say somehow you can find the derivative of rate of y with respect to x and rate of z with respect to y separately, but you cannot find the rate of z with respect to x directly for some reason. So you can use this to find the rate of z with respect to x. Am I making sense? So if you know how to find the rate of y with respect to x, rate of z with respect to y, you can find the rate of z with respect to x by using this formula. If it is not possible to find the rate of z with respect to x directly, but it is the chain rule. So I hope you understand that. So here's an example. Let's say z is root of y, and that y is x squared plus x plus 1. So then the question is, we want to find the derivative of z not with respect to y, with respect to x. Okay? So what's the derivative of z with respect to x? Notice that I have a formula for z, but in terms of y, right? Not x. Now, in this problem, of course, you could say that, I can find a formula for z in terms of x by just plug in by just plugging in this guy here, right? So I can find a direct formula for z in terms of x here, but let's just keep them separate. The derivative of z with respect to x would be, by the chain rule, it would be dz dy multiplied by dy dx. And what is dz dy? Root of y is the same as what? Y to the half, right? So what's the derivative of that? Half y to the half minus 1, right? And if you could do it in the head, that's fine. And then what is dy dx? Dy dx is 2x plus 1, right? So what is that? This is half y to the negative half times 2x plus 1. And I could write this as 2x plus 1 over 2y to the half. And this would be 2x plus 1 over 2 times root of y. And finally, you can plug in what is y. Y is x squared plus x plus 1. So I take root of that. I shouldn't forget about 2. Is everybody okay? So that's the derivative of z with respect to x. Is everybody okay? Any questions? Here's an example. Suppose that you have the following situation. You have a expanding disk. Okay, so you have an expanding disk of, let's use r to denote the radius, and let's denote by a the area of the disk. So let's say this is a disk which is expanding. So and let's say the rate at which the radius is expanding is the following. The rate of change of radius with respect to time, let's say, is 1 centimeter per second. So the radius is increasing at that rate. The radius is increasing at that rate. So the disk is expanding. The question is, what's the rate of A with respect to time? What's the rate of A with respect to time? Am I making sense? So how would we find that? How would we find that? Can I find a formula for A directly in terms of T here? Can you give me a formula for A, area of the disk, in terms of T? No. But can you give me a formula for A in terms of the radius? Okay, what is that? A is pi r squared. Okay, so then what is the derivative of A with respect to time? Well, no. The derivative of A with respect to time is this, by using the chain rule, it is the derivative of A with respect to r multiplied by the derivative of r with respect to time, right? Is everybody okay? What is the derivative of A with respect to r? Now it is what? 2 pi r by using the power rule, and the derivative of r with respect to time is given in the question to be 1. So this would be 2 pi r. If this wasn't 1, then it could have, let's make it 2. That way you know that it's not going to be just 2 pi r. So if this is 2, then I would be getting 2 here, and so I would be getting 2 here, and then I would be getting what? 4. So now the question is, what's the rate of change of A with respect to time? What's the rate of A with respect to time at the time when at the moment when r is, let's say r becomes 100 centimeter. So because the disk is expanding, at some moment let's say the radius would become 100 centimeter. At that moment, what would be the rate? Well, it is just 4 pi times what? 100. And what's the unit for this? Centimeter? Centimeter per second for radius, but for the area, centimeter squared per second, right? Is everybody okay with that? Everybody's okay? All right. So okay. So that's why this notation for the chain rule is helpful in this type of problems. I have to warn you something here. The chain rule says that dz dx is dz dy times dy dx. Notice that it seems like I am cancelling dy, right? But of course, you cannot cancel dy's because this is not a fraction. This is a symbol. They represent derivatives. Even though it seems like you are cancelling out dy's, it's not a cancellation like that. Okay. But it is helpful to remember that this way. Okay, so an example. F of x is 2x plus 1 to the 5. Now, the way I have been doing these problems is that I said you wish 2x plus 1 to be x, so take the derivative assuming that it is x, and then you take the derivative and then you multiply by the derivative of the quantity that you wish to be x. But I'm going to do it a little bit differently now. You wish 2x plus 1 to be x, so what you do is you let y to be the quantity that you wished was just x, and then you let z to be y to the 5. Okay, so notice that then if I want to find f prime of x, okay, then I am basically asking for dz dx, right? I am looking for dz dx. And okay, so then what is dz dx? Well, this is dz dy times dy dx. And what is that? dz dy would be 5 y to the 4, and dy dx is 2. So I get 10 y to the 4, but then if I plug in 2x plus 1 for 10 y, I get this. So that's the derivative. Okay, I'm not suggesting you to find the derivative this way. I'm just saying this is one way I can also write the solution to use the other other notation of the chain rule. Is everybody okay? Okay, so but personally, when I would find the derivative of f, I would just do it the way I have done before. Okay, in one line. So here's another example. I just wanted to show you how the second form of the chain rule could be used. Here's let's say you have a function which is 2x plus 1 to the 5 times the root of x squared plus 1. And you need to find the derivative. First of all, I am going to write this as x squared plus 1 to the half here. So how do I find the derivative? What do I have to do? Yeah, so I have to first of all apply the product rule. So I have to view this function as the product of two factors. And the first factor here is 2x plus 1 to the 5. The second factor is root of x squared plus 1 to the half. So by the product rule, what's the derivative? I take the derivative of the first factor, which is 2x plus 1 to the 5, and then multiply that by what? By the second factor as it is, right? And then plus, I do the opposite now. I have the first factor as it is, and then I multiply by the derivative of the second factor. Is everybody okay? Alright, so in order to find the derivative of the first factor, I have to apply the chain rule, right? So I look at 2x plus 1 to the 5. Immediately I wish 2x plus 1 to be x. So take the derivative, assuming your wish came true. So you take the derivative of that. That would be 5 times 2x plus 1 to the 4. But then you take the derivative of the quantity that you wish to be x. What's the derivative of 2x plus 1? 2. And then you still multiply by x squared plus 1 to the half. Same thing here, you get 2x plus 1 to the 5. And then you multiply by the derivative of x squared plus 1 to the half. Again, you wish that instead of having x squared plus 1, you had just x to the half. So the derivative would be what? Half x squared plus 1 to the half minus 1 by the chain rule, and by the power rule. And then you take the derivative of the quantity that you wish to be x, so which is what? Anyone? Which is 2x. Okay, let's simplify. What I have here is 10 2x plus 1 to the 4 times x squared plus 1 to the half plus 2 cancels out. I have x 2x plus 1 to the 5 times x squared plus 1 to the negative half. Is everybody okay with that? You can leave your answer right here if I ask you to find the derivative only. However, later on in chapter 3, once you find the derivative, you also have to find the values of x for which the derivative is 0. And for that, you need to be able to simplify this expression. Now, how would you simplify this? Well, it doesn't mean that simplification here doesn't mean that you multiply out everything, okay? Simplification here, the way you should do it is the following. Notice that I can factor out 2x plus 1 to the 4, right? Because 2x plus 1 to the 4 would be a common factor of the two terms. So I can factor out 2x plus 1 to the 4. Is everybody okay with that? Are you guys okay with that? Okay. And also what I'm going to do is factor out x squared plus 1 to the negative half. Okay? Is everybody okay with that? I will factor out x squared plus 1 to the negative half as well, because I don't like that negative exponent. Okay? So then what's going to happen? So what goes inside? I have a plus, right, in the middle. Then I get two terms inside the brackets. What would be the first term? Well, I divide the first term by what I am factoring out. So if you divide this, if you divide the first term by what you're factoring out, what do you get? If I divide this quantity by this, what do I get? This and this will cancel out, right? When I divide this quantity, right? So what am I going to get? Let me make sure that you get what I'm saying. What I'm saying is if I divide the first term, 2x plus 1 to the 4, x squared plus 1 to the half, if I divide that by what I am factoring out, so the quantity that I'm factoring out is this. So if I do that division, what do I get? What do I get? 10 times x squared plus 1 to the half minus, you're going to subtract the exponent, right? Half minus half, which would be what? Half plus half, which would be 1. You realize that. When you combine these two, right? When you combine these two, you are going to subtract the exponent in the bottom from the exponent on the top, right? And you're going to get 1. And okay, so what am I going to get from the second term? Well, I'm going to get x times 2x plus 1 to the what? What's that? 1, and then x squared plus 1 to the negative half, x squared plus 1 to the negative half cancels out, right? So that's exactly what I'm going to get. You realize that? If I divide the second term by the quantity I'm factoring out, I get exactly x times 2x plus 1. Is that making sense? Okay, so let me erase that. And now this would be 2x plus 1 to the 4, and the negative exponent I'm going to write in the denominator. And then here I get basically 12x squared plus x plus 10. Is that okay? Everybody's okay with that? So that's how I would simplify this. Now, the reason it is nice, now if you're asked to find the values of x for which the derivative is 0, so basically if you want to know the values of x for which this quantity is 0, is it easy to do now? Well, yes. This quantity would be 0 if either 2x plus 1 to the 4 is 0 or the quadratic is 0, right? And then I know how to solve a quadratic equation. I know how to solve 2x plus 1 to the 5 is equal to 0. So we're going to see those things later. But okay, any questions? Okay, this is all I had to say about chain rule. When I reviewed trig functions, At some point, I didn't review the graphs of the trig functions, right? But then I uploaded a video on graphs of trig functions in Moodle, and I asked you to look at that at that time. If you didn't do it, it's probably a good time for you to review that, okay? And so I'll assume that you have done that and reviewed the graphs of these trig functions. Okay, so the next topic is, remember chain rule was in section 2.5. Now I'm going back to 2.4. And this is on derivatives of the trig functions. Okay. The derivatives of trigonometric functions. To compute the derivatives of sine, cosine, we need okay, if I find the derivative of sine and if I find the derivative of cosine, can you find the derivative of the other trig function? How? So suppose you know the derivative of sine, you know the derivative of cosine. How would you find the derivative of tangent? You write tangent as sine over cosine and then you apply the quotient rule, right? So my point is, once you know the derivative of sine and cosine, it's easy to find the derivative of the other trig functions. But finding the derivative of sine and cosine takes a little bit of work. Those of you who remember the derivatives of sine and cosine, for just today's for this week, assume that you don't remember that. So to find the derivatives of sine and cosine, there are two limits that we need to compute. One of the limits that we need to compute is the limit as theta goes to 0 of sine theta divided by theta. And another limit that we have to compute is the limit as theta goes to 0 of cosine theta minus 1 over theta. A long time ago, when I was talking about limits, I told you that the limit of sine theta over theta was what? As theta goes to 0. I told you that this limit is 1. I didn't give you a justification for that. I stated that as a fact. Okay, why this limit is 1? I didn't justify that. And the limit 2 here turns out that this limit is 0. So I'm going to show you why in a second. Everybody's okay with that? Okay, so first of all, I'm going to justify number 2. So proof of 2. So you're looking at the limit as theta goes to 0 of cosine theta minus 1 over theta. We are going to assume that we already have justified number 1. So we can use 1 in this one. How do I compute this limit? If I plug in 0 for theta, what do I get? If I plug in 0 for theta, I get 0 divided by 0. However, remember that what trig did we apply before? We factored out, we rationalized to get rid of the factor that's giving me 0, right? They will not work here. But something similar to rationalizing is going to work here. What? Well, in order to find this limit, the trick is you do something similar to rationalizing, which is you are going to multiply this by what? Cosine theta plus 1 over cosine theta plus 1. Now let's see what happens if you do that. If you do that, what happens is that in the denominator you are going to get theta times cosine theta plus 1. In the numerator, what are you going to get? Cosine squared theta minus. So if you multiply the numerators by using FOIL, you are going to get cosine squared theta minus 1. Can you express the numerator in terms of sine? Remember this identity, sine squared of theta plus cosine squared of theta is 1, right? So from this, what is cosine squared of theta? Minus 1. Negative sine squared of theta, right? You guys agree with that? So using that, then I could say that this is the limit as theta goes to 0 of negative sine squared of theta over theta times cosine theta plus 1. Okay, what can I do now? Remember I said I'm going to use number 1. So in order to use number 1, what I have to do is the following. I have to rewrite this as sine theta divided by theta. And what's left? Cosine theta plus 1 and negative sine theta, right? You guys agree with that? Now we are almost done. Notice that what's the limit of sine theta over theta as theta goes to 0? By using number 1, I know that it's got to be 1. What's the limit of the second factor here? 0, because when theta is 0, what's the limit of the denominator? As theta goes to 0, the denominator goes to 1 plus cosine 0. Cosine 0 is 1. So the denominator here has limit 2. The numerator has limit, sine 0 is 0. So I get 0 over 2, which is 0. So I know that this guy has limit 1, this guy has limit 0. So together the limit is 0. Everybody's okay? So what we have justified then is that the limit of cosine theta minus 1 over theta as theta goes to 0 is exactly 0. So we justified number 2. Is everybody okay? Do you need time to write it down? Anyone needs time to write it down? Okay, so now the harder part, which is justifying number 1. Before I start that, let me remind you something. If I have a circle of radius, let's say r, the circle has radius r, and let's say I take a slice of the disk of radius r, so that slice, and that slice is subtended by the angle theta. Can someone tell me what's the area of that slice? What's the area of that slice? I reviewed that when I reviewed trigonometry. What's the area of this slice? What's that? Yeah. No. Almost there. The way you want to remember this is that take the area A divided by the area of the entire sector. So what is the area of the entire sector? By entire sector, I mean the entire disk. The area is pi r squared. Pi r squared. And that's going to be the same as what angle subtends the sector that I have. The angle theta subtends the sector that I have. And what angle subtends the entire sector? So that's 2 pi. So from here, if I solve for A, what do I get? I would get half, pi cancels out, right? I would get half r squared times theta, right? So the area of a sector of a disk of radius r subtended by an angle theta is half of r squared theta. Is that making sense? The area of the sector sector subtended by the angle theta is given by that. Okay, so we are going to use that in proving number 1. So proof of 1, and what we need to use there, we are going to use the squeeze theorem. Okay, we are going to use the squeeze theorem. Okay, so let's say that I have the circle of radius 1, which is the unit circle. So it is centered at the origin. It is centered at the origin. Okay, so we want to look at the limit as theta goes to 0. So because theta goes to 0, I can assume that theta is very close to 0. And if theta is close to 0, then theta could be positive or negative. So the terminal side of theta would be in which quadrant? If theta is close to 0, positive or negative, the terminal side will be either in the first quadrant or the fourth quadrant, right? So assume that theta is positive. So then the angle would look like this, right? So that's the terminal side of the angle theta. And once I have that, I am going to make a vertical line here. And the vertical line intersects the terminal side at this point here. Let's call this point here, let's call that O. This point here, let's call that P. This point here, let's call that Q. I am going to join the points P and Q as well. Okay, and let's call this point R. Is everybody understanding the picture? Okay, I have the angle theta. From the point Q, I made a vertical line until it intersects the terminal side of theta, and the intersection is R. Okay, if I now say that the area of the triangle OPQ is that less than or equal to the area of the sector OPQ, because the sector OPQ includes the triangle OPQ, and that's less than or equal to the area of the triangle ORQ, right? You agree with that? Because ORQ includes the entire sector OPQ, right? Is everybody okay with these two inequalities? Everyone's okay with these two inequalities? Okay, can someone tell me what's the area of OPQ? What's the area of OPQ? Well, let's say the height of OPQ is h. So this would be what? Half of h times the length of the base, which is what? Which would be the length of OQ, yes? less than or equal to area of the sector would be what? Half of r squared times theta, right? But what is the radius here? The radius here is 1 because I took the unit circle. And what's the area of ORQ? The area of ORQ is the length of RQ multiplied by the length of OQ, right? Is everybody okay with that? You guys are all okay with that? Give me just 1 minute here. And notice that I can multiply everything by 2, and the length of OQ is what? Length of OQ is 1 because it's a circle of radius 1. Length of OQ would be 1. So then I can say this is h less than or equal to theta less than or equal to the length of RQ. Everybody is okay with that? Yeah. Everybody is okay with that? Very quickly, can someone tell me, remember this angle here is theta. Can you express h in terms of sine theta? Notice that h in the right triangle that I have here, the small one, h divided by, h is the opposite, divided by OP is the hypotenuse, would be sine theta, right? But what is the length of OP? Length of OP is radius, which is 1. So I know that then h is what? H is sine theta. And what can you say about RQ? What can you say about RQ? Anybody? I don't want to use RQ is the opposite for the bigger right triangle. RQ is the opposite of theta, but I don't want the hypotenuse, the length of the hypotenuse I don't know. So I don't want to use that. Instead, notice that if I look at RQ divided by OQ, then that's what? That's the opposite over adjacent, and I should be getting what? Tangent of theta. But again, OQ is what? 1. So I know that RQ is exactly tangent. So I know that RQ is exactly tangent of theta. And notice that this is, I'm almost done. This is sine theta less than or equal to theta. This is sine theta divided by theta. Sorry, cosine theta. And what I'm going to do now is divide everything by sine theta. So if I divide everything by sine theta, I get 1 less than or equal to theta over sine theta less than or equal to 1 over cosine theta. And now I'm going to flip everything. So if I flip everything, I get sine theta over theta. And if I flip here, I get cosine theta. Now notice that that's the same as saying cosine theta is less than or equal to sine theta over theta less than or equal to 1. What's the limit of this guy as theta goes to 0? 1. What's the limit of this guy as theta goes to 0? Cosine 0 is 1. So that forces the limit of the middle one, to be what? 1 as well. Okay, so that's how the limit of sine theta over theta is 1.